In this section, we're going to start discussing something we haven't worried about. So far, we've been dealing with points. So we're asking the question about equilibrium of points. And points have no dimensions. They're non-dimensional. They're just a point. And as such, they don't rotate. And so we're going to now introduce the concept of rotation and quantifying how forces create rotation about a point. All right, so to sort of set the stage, let's think about a wrench. So here's the bolt head. All right, so for those of you that have never used a wrench before, you may need to go to the internet and catch this. And here's our wrench, right? So fits around the bolt, sort of a bad way. All right, and for those of you that have ever tried tightening a bolt, you know that if I grasp the wrench very close to the bolt and attempt to pull it, right, it takes a lot more force to create the rotation than if I grab it way out at the end here and pull it. So what I'm trying to do with the wrench, right, is I'm trying to rotate the bolt this way. And ideally we rotate about the center of the bolt, right? So this rotation occurs about this center point. And if I pulled it really close to the bolt, it takes a lot more effort to turn that bolt than if I hold it way out towards the edge of the wrench, right? And this even more drastic examples, if I got real close in here and I grabbed hold of the bolt by my hand and tried to twist it, it's not very easy to do, right? And so we think of this, right, as let's say, right, here's D1, and then here is D2, and so our twisting force, right, we'll just call it twisting force for right now, is greater at F2 than F1. Okay, so the whole point of this sort of example here is to drive home the fact that even if F1 is equal to F2, its tendency to cause rotation about point A right here is different depending on how far away from point A that force is applied, right? So F1 here is applied close to A, and so its twisting force is less than the twisting force applied at F2. And this twisting force we call a moment. Okay, and a moment is the tendency for a force to cause rotation. So the moment of force 1 would be a measure of the tendency or the intensity of its ability to cause rotation about A. All right, so that's the whole point, right? We're trying to say, we know that, right, our intuition tells us if we pull at F1, right, this will want to rotate about some point, and if it didn't, screws and bolts wouldn't work. And so the thing we want to do is somehow quantify how much tendency to rotate that force is going to generate. And we call this value that we're going to use a moment. All right, but a moment is now a little different, right, than a pure force vector. We need to think about a moment. We need two things, right? A moment, we ask two questions. One is how big, and that we think about as magnitude, right? How big, what is the magnitude of the twisting? And two, what is the axis of rotation? All right, so that's the two things we want to know. We have our bolt here, right? Here's our bolt. And when we apply our force, our moment, our force due to a wrench, right? We know that we want it to rotate about that axis, right? And we want to know some sort of magnitude. So how do we do that? Well, there's a mathematical vector operation called a vector product, and we answer those questions with the vector product. A cross B equals C. Okay, and we think about this as this is the way, the sort of geometrical interpretation of this. A, B, right? There's an angle between them, and they generate that vector C is 90 degrees to the plane that A and B makes. This is maybe a little complicated, but you can think, right, 3 points make a plane, right? So A and B always define a mathematical plane that you run through these 3 points. And this vector C, when you cross those things together, when you cross A and B together, gives you a vector that has a magnitude and is perpendicular to the plane of A and B. So right here we've answered both questions. We've got a magnitude, and now we have an axis perpendicular to the rotation. Perpendicular to the plane of A and B, which makes sense, right? Because keep in mind our wrench example. All right. We're rotating about this axis, which is coming out of the board at you, right? So we apply F, and so we have some sort of distance D, right? So naturally, we're thinking some sort of vector operation between D and F is going to get us the magnitude of the rotation. The magnitude of C is given to us by the magnitude of A times the magnitude of B, sine the angle between them, sine theta. Okay, so these are the two sort of critical vector operation things. Your book has a description of how to calculate A cross B. It's a little more complicated than just standard, and this is pretty straightforward right here. Okay, so we know the vector product is going to come into play here, right? And we're going to go ahead and define our moment now as the moment vector M is equal to the distance R crossed in the distance F. And this is a moment about a point A, and this is a vector, a position vector from A to the force in a very specific way. So let's think about point A right here. So I am interested in point A, and here is force F. And so the position vector we're going to write is from the point that we're interested in to some line of action on the force. So I can think about creating a infinite line that sneaks out all the way along here, right? And I can then draw a position vector to any point on this line and calculate a moment. The moment that I will get at R1, RAF, R2, and R3, so it doesn't matter, right? R2 cross F equals R3 cross F equals, and so on. Doesn't matter what one we use. We will get the same moment value. Okay, so that seems a little counterintuitive right now. You're a lot of people, I know this gave me trouble when I was thinking like, wait, no, how could that possibly be? Well, there's a quick way to think about it that'll get you sort of a proof of this. All right, so here's our point A. Here's our force F, and here's a line, right? The line that goes along that force all the way there. Let's think about two vectors. Let's think about this vector R1 and this vector. Let's be a little less specific. This vector R2. Okay, R1 we can write as R2 plus a vector R3, right? That makes sense. So there's nothing special there, right? We just took two vectors, right? We broke this into R1 and R2. We can then think, right, R1 cross F must be equal to R2 plus R3 cross F. And then R3 here, we can break it into, or rather we can then distribute the cross product through this addition. So there's a here, let me see if I can move this all over here. Chances, oh, that's working. Yay. There we go. Let's move it. Okay, great. Awesome. All right. So we can write, right, R2 cross F plus R3 cross F. All right. let's look at R3. This, right, R3 is parallel to F. And since if we think about the R magnitude, right, R3, F, sine theta, the angle there is 0. So this whole thing becomes 0 because sine of 0 is 0. And so R3 cross F is 0. And so R2 cross F must then equal R1 cross F, because this additional piece that lies along the F force to get to the same place, the cross product between F and R3 has to be equal to 0. So that's a real quick proof of the fact that we can draw R1, R2, R3 anywhere. R1 and R2 will both give you exactly the same cross product that that we might be interested in. All right. So let me erase this and rewrite this again. So we calculate a moment by saying M is equal to R cross F, and this moment is about a point, and so we pick a point A, right? So this would be moment about A. We have our force F, and we can draw our position vector R from A to the force, any line on the force, to calculate our moment. All right. We've said from the previous thing we said, right, any value of or any particular R value, R that we want to choose, will give us the same moment. So there might be a sort of some special cases that we should be interested in. And one of those particular special cases is, what we're going to do is we're going to assume that the R makes a 90-degree angle to the force that we're interested in, R times the F, right, to A. So this makes 90 degrees. This is the vector there. So that means, right, we have here, in this case, we have R cross F. So the magnitude of this value is going to be given to us by the magnitude of R cross F sine 90 degrees. That's equal to 1. And so the magnitude of R cross F, or the magnitude of the moment vector, is just now given by magnitude R times F where R is perpendicular to F. And R has a special name, right? We just call this D. So that gives us F times D. So for any vector that's 90 degrees, we can just simply multiply F times D, and we get, or the magnitude of the distance, and then we get that moment. The direction of this moment, so this, right, obviously has a tendency to cause rotation this way. And so we would use what's called the right-hand rule to figure this out. This is impossible. Unfortunately, the right-hand rule is impossible to show you on here, so we'll have to talk about that in class. But that's the technique that you'll use to get that. So again, the two things we have here, we introduce moments, and those are R cross F equals the moment. We also know that the magnitude of the moment is equal to D times F, where D is perpendicular to F from point of interest. That's it. All right. The vector product has a couple of properties, so let's talk about those real quick. So properties of vector product. So it is not commutative. That means R cross F is equal to minus F cross R. So keep that in mind. Don't swap these because you'll get a negative value. It is distributive with respect to addition. So A cross B plus C is equal to A cross B plus A cross C. Notice I preserve the order of the cross product. And it is not associative. So A cross B cross C. So A cross B cross C does not equal. A cross B cross C. Of course, you could think about special cases where this might be true, but in general it is not. And so that's the critical thing that we need to be aware of. All right, so the two that are most important really is this not commutative part, right? So this is actually called anti-commutative. And so that means R cross F is defined this way. Don't flip them, because otherwise you'll get a negative answer. All right, and that's it. Again, there's several ways to calculate the cross product. Those are covered in the book, and you can look those up, and we'll talk about those in class as well. All right, thanks much.